Good morning, ladies and gentlemen. Welcome back. I just want to let you know that there's construction going on, so you might hear some loud drilling sounds throughout the video. I hope it does not bother you. Um, it definitely might distract me, but I'll try to get through. So anyway, today we're going to discuss this idea of something called slope fields. How do we construct them and how do we use them to analyze differential equations? But before we get into the lesson, I'd like you to warm up by finding the general solution to this differential equation. Okay, welcome back. I'm hoping you paused and attempted at least, and maybe you were struggling to solve this differential equation because you should have struggled. This is not a separable differential equation. So a little bit of a troll action going on here. My apologies. But I did this just to sort of motivate the use of something called slope fields. So there are situations where differential equations can't be solved by the means we've discussed, by separating the variables, right? So like for example, for this particular differential equation, let's attempt to separate these differentials. So the idea is we want to get all the x variables on one side and all the y variables on another side. Well, looking at it, I mean, one thing I can do is like, okay, let's multiply by dx. Well, what happens when we multiply by dx? We have dy is equal to x plus y times that dx. And the issue is this y is now trapped inside of this product, right? X plus y is a binomial, and that entire binomial has to be multiplied by dx. So you can't really isolate the y. You can't pull that y out without first either distributing the dx, and there's the construction sound. Maybe you hear it. Hopefully you don't. But you can't separate these variables without either distributing the dx or dividing by dx, and dividing by dx would just undo what we did. All right, so that is not going to work out. Let's say we start with the right side and we try to move x or y over to the left. Well, let's see, I can subtract both sides by y. So my left side would be dy dx minus y is equal to x. Okay, that's great. I have x alone, but on the left side I have a dy and a dx and a y. So this doesn't work out. Okay, this doesn't work out. So there's really no way that we can separate these differentials. However, it's not that uncommon for in physics, let's say, for some particular model to have this rate, for a particular some kind of a movement rate to be defined in this way. There's nothing too strange about that rate of change, okay? And so this is a situation that still could be studied in practice, or still could be seen in practice, and needs to be studied in some way. And so how do we study if we can't determine the general solution? Well, we still have information about this model, and that is that the slope at any point is equal to the sum of x and y. And we can use that information to draw something called a slope field. So I'm going to scroll down. Again, excuse the construction going on. I apologize about that. Nothing I can do. But what you're looking at here is indeed the slope field for this differential equation. Now it looks kind of crazy, but it's actually it's pretty simple. All we're doing is we're going to each and every point on the plane, and whatever that point is, let's say we choose this point. This is the point, it looks like 1, 1. what we're doing is we're taking that point, we're plugging that point into the differential equation. So dy dx at 1, 1 will equal 2, right? That's 1 plus 1. And then what we literally do is at that point, we draw a little line segment with a slope of 2. Okay? And we repeat this process for many, many, many different points. Or when I say we, I'm referring to computers. Computers will actually handle this job. As humans, this would be a really tedious task. And so that's why for this topic, you'd really only be asked to create a slope field of 9 points or 12 points, nothing too crazy, nothing like this, definitely not. But just let's go through a few more examples so it makes sense. So I'll choose another point here. Let's say this point here. This point is around, looks like negative 1.9 comma negative 2.1, something around there. And so when I plug that point into our differential equation, right, dy dx evaluated at negative 1.9 comma negative 2.1, that is going to equal, it's going to just equal the sum of these two, excuse me, it would equal the sum of these two numbers, which would be negative 4. And that, again, that number is the slope of a curve modeled by this differential at this particular point. So if one of the particular solutions goes through this point, negative 1.9 comma negative 2.1, and is modeled by this differential equation, then that curve will have a slope of negative 4 at that point. Okay, so basically what you're looking at is essentially the general solution. So when we have a non-separable differential equation, the way we look at the general solution is by studying the slope field. Now the question is, well, what if we knew the rate of change and also we happen to know some initial condition? Can we get a sense of the particular solution? Well, yes, you can. And we will use the slope field to help us determine what the particular solution looks like. We might not necessarily be able to get the exact equation of the particular solution, but we can get a sense of what the model would look like. So for example, here we have the same differential equation, but let's say we happen to know that f of 0 is equal to 2. In other words, the point 0, 2 exists in this model. Well, that being said, I can use the slope field to sort of guide me to what the particular solution looks like. So I would start here at the known point, and then I would use the rest of the information that I see on the plane to sort of guide what the rest of the curve looks like. And I do that by just sort of following the direction of the slopes. So to the right of x equals 0, the slopes are basically facing upwards, heading upwards. So I would draw my curve in that direction, right? The slopes tell me the direction that the curve is pointing. Now, as I move to the left of the known point, well, at first, the y values are pointing down, and then notice the slopes start to flatten out a bit, and then they start heading up and to the left. And so that's why our particular solution might look something like this. Okay, so there you have it. That's essentially it. That is the idea behind a slope field. We use them to analyze differential equations that we can't solve by using our separable differential equation skills. Okay, we cannot separate every single differential equation, so we need to use whatever information we have available to us to study either the general solution or the particular solution. I want to show you another example. And we're going to sort of work backwards, and we're going to use a situation that we're familiar with just so you see what a slope field looks like, even in a situation that you're familiar with. So let's say you're given x squared plus y squared equals 25. Just as an exercise, I want you to see if you can determine dy dx. So determine, based on this particular solution, determine the differential equation. All right, so I'm going to allow you a moment to just pause me and attempt this problem. Okay, welcome back. Again, assuming you attempted this problem. Well, the way we determine dy dx based on a given equation is we have to differentiate. Since x and y are sort of like intermingling, mixed together, we're going to have to use implicit differentiation. So we're going to differentiate with respect to x. So the first term is simply 2x. The second term will be 2y times y prime, or dy dx. Right? And the reason is that we're using the chain rule because y is some implied function of x. So when we take the derivative of y, we need to multiply by the derivative of the inner, and that would be dy dx. The right side, that's just a constant, and so that's going to equal 0. So notice when we differentiate, we actually sort of take away all the information of the initial condition. So what we're going to end up getting when we solve for dy dx is something that looks like, so dy over dx equals negative x over y. And so notice this is a differential equation. It is a separable differential equation, so we could sort of go backwards and solve to get the equation of the circle. Again, though, there is an initial condition built into the fact that x squared plus y squared equals 25. That tells us the particular circle we're dealing with, but after differentiating, we lost that information. So we're just going to use the general differential equation and pretend we don't know how to separate differential equations and solve. So what we're going to do is we're going to build a slope field for this differential equation. And I'd like you to, before I scroll down, like try to guess what it might look like. Remember, this differential equation came from this original equation. Okay, and as you know, that is the equation of a circle. So try to guess what the slope field might look like. All right, scrolling down. And if our differential equation is dy dx equal to negative x over y, then hey, this is what our slope field looks like. And as you can see, it looks like the curves that match this slope field, or that are defined by this differential equation, they seem to be circles, and that is indeed the case. Right? So you see a whole bunch of sort of concentric circles inside of this slope field. All right. Now the thing is, this is like the general solution. This is what every curve with this differential equation might look like. So this is the family of solutions, basically. Now, remember, going back here, we were actually dealing with this particular solution, x squared plus y squared equals 25. So for example, what that means is the point, let's say 3, 4, exists on this curve. So that might be an initial condition that we use. All right, so I'll show you what that looks like if we're given an initial condition on this slope field. Scrolling down, and again, let's say we know the fact that f of 3 equals 4. So what we would do is, just like before, we start at our known point, and then we use the information that is told to us by the differential equation to sort of draw the rest of the curve. And I'm not saying this is an easy thing to do. It's not very obvious, like, exactly how closely do you have to follow the curves. The point is that what we will do is get something that is kind of close to the model. And obviously, the more slopes you draw, the better idea of what the particular solution looks like you'll have. All right. Now, I happen to have known already what the equation was for this curve, and so this is the perfect circle But in general, you know, we won't be able to work backwards like this. We'll be given a differential equation that we can't separate, and we can only rely on maybe an initial condition and the slope field. So all you have to do is just do your best to sort of go with the flow. What is the slope field telling you? And that's that. So I'm going to be posting, I'll post an assignment, which you'll practice some of these problems. I'm going to leave it there today. If there are any questions, please come to SGI, and we will, in all likelihood, spend one more day on this concept, as it does seem to be a bit of a confusing topic for some. So, you know, if that is the case, don't worry, do your best. And of course, ask questions. That's really the best way to clear up any confusion you might have with anything. Okay, so we'll leave it there. Ladies and gentlemen, I hope you're all doing well, and I will talk to you soon. Be well, everybody. Bye.